I want to talk today about different types of intermolecular forces, and we're going to be looking at 4 different intermolecular forces today. The first one I want to talk about are ion-dipole interactions, and these are illustrated here by looking at sodium chloride and Na+Cl- dissolving in water. And as you might guess from the name, this type of interaction involves an ion, or ions, interacting with a dipole. So the positive region of sodium interacts with the negative part of I should say the positive of the Na plus ion interacts with the negative region of the water's dipole, and the negatively charged chlorine ion interacts with the positive region of water's dipole. This is the interaction that allows water to dissolve sodium chloride, and it's a rather strong intermolecular force. The next intermolecular force I want to talk about is the one between dipoles. So this is a dipole-dipole interaction, and it's shown here for formaldehyde. And what we have here are the negative and the positive end of formaldehyde's dipole interacting with other positive and negative dipoles and other formaldehyde molecules. This is not as strong an interaction as the ion-dipole interaction, but it is still significant in elevating the boiling point, melting point, and affecting other properties of molecules. You need, for this type of interaction, some sort of polarized bond. In this case, we're looking at a carbonyl with a C double bond. The O is polarized with a positive on the carbon and the negative on the oxygen. The next type of interaction I want to look at is, give me a second, the one that's called hydrogen bonding. And in hydrogen bonding, what we have are atoms bonded to other electronegative atoms, or let me be more specific, we have hydrogen bonded to other electronegative atoms that generate a very strong interaction between a lone pair and those hydrogens. So I'm showing 2 different examples of this. For ammonia, NH3, I'm showing the nitrogen, which is an electronegative atom, interacting with a hydrogen. And I'm showing the lone pair on hydrogen interacting on nitrogen interacting with the hydrogen. This is a particularly strong interaction because the hydrogen atom bears a substantial amount of positive charge character. It only has 1 pair of electrons, and that nitrogen, since it's more electronegative, is pulling those electrons away from the hydrogen. So, as I said, there's a lot of positive charge character on those hydrogens, and it interacts well with the nitrogen. It's a lone pair of electrons. The lone pair of electrons is called a hydrogen bond acceptor. This hydrogen is called a hydrogen bond donor. If we look at the interaction between water and formaldehyde, formaldehyde has a hydrogen bond acceptor, the oxygen's lone pair, but it doesn't have any hydrogens bonded to polar atoms. So it can't donate a hydrogen bond, but it can interact with the hydrogen bond donor on another molecule like water. In general, the hydrogen has to be bonded to a nitrogen, oxygen, fluorine, and in some cases sulfur for effective hydrogen bonding. The last, or to be effective hydrogen bond donor, the last type of interaction I want to look at is this one, and it's slightly out of the screen. It is something called London dispersion forces. These are relatively weak interactions caused by temporary fluctuations in electron clouds generating temporary dipoles. I'm showing the example here for bromine. The more polarizable an electron cloud is, the stronger this interaction is. So fluorine holds its electrons very tightly, not very strong interaction. Iodine, much more polarizable, much better LDF.